A team of scientists at North Carolina State University has developed two butterfly-shaped soft robots, capable of swimming at 1.7 and 3.74 body lengths per second. They are being referred to as the fastest swimming soft machines in the world because until now, soft robots were known to swim at a maximum speed of 1 body length per second. What's more interesting is that the design of the butterfly bots is inspired by 3 different types of sources: metal snap hair clip, an accessory that is commonly used by girls to bind their hair, butterfly stroke, a swimming style performed for fast body movement in the water, and the manta ray fish, which is a fast-swimming saltwater animal. A soft robot is made of soft materials such as elastomers, gels, or memory shape alloys. For such robots, swimming is more complex and challenging because it involved facing large water resistance and interactions with the fluids. The compliance of the soft materials results in a small force output, which eventually makes it challenging for the robot to swim fast, which needs a larger thrust force. In contrast, marine animals like the manta rays are able to swim fast, and that too in an energy-efficient way. This is because it can swim with Struhel number falling in a narrow range of 0.2 to 0.4. Struhel number is related to wing flapping frequency, amplitude, and swimming speed. Mathematically, it is the ratio of the product of flapping frequency and amplitude to speed. A higher flapping frequency may lead to a higher swimming speed, but it does not necessarily render a high power efficiency since it consumes more energy. Only when the ratio or the number falls in a range of 0.2 to 0.4, it can give a peak propulsion efficiency and thus a power efficiency. The motion of most flying animals and swimmers is in this range for saving energy. However, in the case of soft robots, both the materials compliance and the narrow range of natural selection of swimming performance make it challenging to achieve high speeds and energy-saving behavior altogether. The researchers designed 2 soft robots. One can swim fast but can only swim in the forward direction, like the butterfly stroke. The other soft robot can take fast turns but has a low swimming speed. The faster butterfly bot uses its body to simultaneously actuate the flapping of a pair of wings. The maneuverable bot employs 2 side-by-side body movements to independently actuate either wing. So, when the left wing is flapping while the right wing does not, it will take a right turn or vice versa. When both wings are actuated to flap simultaneously, it will swim forward, like the faster bot. However, its speed is slightly sacrificed due to the increased body weight. To overcome the small force in both the soft robots, the researchers adopted the concept of snapping, a fast motion observed in the fast closure of hair clips and the Venus flytrap. Similar to a hair clip, the wings of the bots are bistable, meaning they are stable in 2 different positions. The bistability factor speeds up the response of wings and increases dynamic flapping forces, and it also saves energy, since it is like a pulse force. Interestingly, the Struhel numbers for both butterfly bots fall between 0.2 to 0.4. But there is a catch. The butterfly bots are made of silicone and their bistable wings require an air supply to switch from one stable state to the other during swimming. The air is pumped from an external source into the air chambers of a bot's body. The chambers inflate and deflate and further enable the wings to snap back and forth accordingly. This means that the butterfly bots are not free-swimming robots. They operate while staying attached to slender tubes that supply air. The researchers are currently working to make the bots untethered through onboard power and control. They believe these changes could also further improve the robot's speeds.